My name is Cherish Bauer-Reich. I am the chair of the engineering department at the University of Jamestown. I co-authored this paper with my colleague, Dr. Katrina Christensen, also from University of Jamestown, and we're discussing a preliminary study to define limits of active learning strategy effectiveness in physics courses. The research generally shows that active learning strategies where students engage in problem solving during class tend to work better than the traditional approach of lecturing, which is kind of considered a passive form of teaching. So when we were doing this research, we made the assumption that active learning strategies are working better, and we wanted to know if there was a difference between the different active strategies that could be employed. The classes that we used for this research were the 143 and 144 class, as well as the 203 and 204. 143 is an algebra-based approach to kinematics and mechanics, so that talks about kinematics, forces, momentum, etc. 144 is algebra-based optics and electricity and magnetism. 203 and 204 are the calculus-based equivalents of those courses. So 203 deals with mechanics and kinematics, 204 deals with electricity, magnetism, and optics. In the 143 and 144 classes, the students taking those typically were upperclassmen in biology and exercise science. Most of the students are women, and initially coming in, a lot of them had not had physics, so their scores on the pre-tests were often lower than in 203 and 204. The 203 and 204 classes primarily are composed of engineering students. We also have a handful of pre-professional chemistry and math students. They tend to take 203 in the spring semester of freshman year and 204 in the fall semester of their sophomore year, and most of the students are men. Overall, these classes are very small classes. Typically 143 and 203 are slightly more than 20 students, and 144 and 204 will have less than 20 students. There's a lot of interaction because of the fact that they're small, but because of the fact that we have a small student body, we weren't able to provide a control group for any of these. Additionally, I wanted to mention that student evaluation scores were included, not necessarily to give any credence to how much they learn, but to express how frustrated students might be with a particular learning style. The three types of active learning that were presented in the classes were interactive lecture, problem-based lecture, and flipped class. The interactive lecture basically proceeds as a normal lecture where the instructor talks for a little while, but then occasionally will throw up a problem for the students to work on in class. One example is the think, pair, share method, where the instructor throws a problem up, perhaps a multiple choice problem, presents it to the students. The students are given a couple minutes to think about it themselves, and then to discuss with another student. Then at the end of this, the instructor will ask them to give their answers, and if a large number of students don't seem to be understanding the concept, then the instructor can spend more time on the concept. However, if the students generally seem to be getting it, they can move on to the next concept. In this case, the interactive lecture also utilized homework outside as a reinforcement technique. Problem-based lecture is very similar to the interactive lecture. It uses similar principles, but rather than discussing theory and concepts and working towards problems, it basically describes all of the concepts in terms of its usefulness in solving problems. As an example of this, if you were doing a problem, for instance, on momentum, you would say, hey, we have two train cars that are rushing towards each other. What's going to be the final momentum of the system after they collide? Then you would go through and you would introduce the concept of momentum, demonstrate how to solve the problems, etc. In this case, the problems that were discussed in class were used later as the basis for a quiz. So in a matter of 2 days, if you went over about 10 problems, the students would be responsible for knowing all of those, but they would be given a quiz in class that would only cover one. So they wouldn't necessarily know which problem they'd be quizzed on, but they would have to know all of them and be prepared for the quiz. And that was used in place of doing homework outside of class. The final method being used was a flipped class. In this case, students were responsible for reading material from the book and potentially watching videos that were assigned, and then they would have to take a reading quiz before class. So they had to come to class having at least some familiarity with the material. They would then during class be given problems to do, and they would work collaboratively in groups to solve the problems. The problems would be discussed after everyone had had time to work on them, so that students could get a sense of what they had done wrong and where their misunderstandings were. In this case, homework is also used as a reinforcement, so they were given homework sets to do and turn in later. There were 2 exams that we used to do these assessments. The first one is the Force Concept Inventory, and that basically measures the understanding of kinematics and Newton's laws. All of the questions are multiple choice questions, and it doesn't include any concepts from energy or momentum. The second semester, so 144 and 204, we used the Conceptual Survey of Electricity and Magnetism, the CSEM, and that basically looks at electricity, magnetism, and associated concepts like electric potential. One measure that was used to assess the tests was normalized gain. Normalized gain takes the number of problems on average that the students got wrong when they took the pre-test, and then looks at how many of those they then got right when they took the post-test, and it takes it as a fraction. So if a student got 20 problems wrong initially out of 30, then when they took the test again, of those 20 problems they got 5 correct, then you would take 5 out of 20, or 25%. You can see that if they got all of those initially incorrect problems correct when they took it the second time, they would get a score of 1. So all of the scores are normalized out of 1. So a small gain generally is considered less than 0.3. That's typically what people see when they do just a traditional passive lecturing course. In interactive learning strategies, you get a medium score generally from 0.3 to 0.6, and large gains tend to be 0.7 or above, and those are the types of results you would expect to see from something like a studio physics class. Okay, the other measure we used was effect size, and effect size is basically the difference between 2 means. This gives you an idea of, if you have 2 groups of students, how easily you can tell which group they came from based on their score. This measure removes the effect of small groups, so basically what you do is you take the difference of the means between the 2 groups and you divide by the standard deviation. A small change is generally 0.2, a medium change is 0.5, and a large change is 0.8, but the number that you generally see is less than 2. So you can see that the scaling on this is slightly different than with the normalized gain. That being said, this is a good use in our case. You don't see this as much in the physics literature, but because we have small groups, we chose to include both of these values. When looking at the data, it wasn't really clear how to group the data to get some sort of clear result. You can see here that it was grouped by the approach, and that didn't really provide any sort of conclusive result. I also looked at the exam to see which exam worked better. That didn't provide anything conclusive. The best way to look at the data actually seemed to be to break it up in terms of the class. So here we have the algebra-based class. Over here we've got the calculus-based class. And as far as the scales, you can see down the left side of both of these we have the normalized gain and effect size. On the right hand we have the student evaluation scales. So that works for both of these. So when looking at this, the 100-based class, we've got the kinematics classes here. You can see that the problem-based lectures were more effective and that the students actually preferred them to the flipped class. When we look at the electricity and magnetism, you can see that normalized gain and effect size weren't terribly different. There was a slight improvement with the problem lecture, but again, the students really preferred these classes. So for the biology-based students, the problem lectures seem to work much better, and some of this may have to do with the fact that they're upperclassmen. If we go over and we look at the calculus-based, we have the mechanics types classes over here. You can see that the problem lecture was the most effective and the interactive lecture was the least effective, with the flipped class being in between. Interestingly enough, the normalized gain for both of these classes was really similar, but the effect size was fairly different. So this is one question that kind of came up to me was, well, which is the better measure? When you look at most physics literature, they tend to focus on normalized gain, but maybe effect size is a better measure. That being said, the students actually preferred the flipped class to the problem lectures. So they either didn't like the memorization or they preferred the interactivity of the flipped class. If you come over and you look at the electricity and magnetism class, you can see that the results are actually flipped. The flipped class actually seemed to work better by both measures than the problem-based lecture. However, interactive lecture was still less effective. So one thing that is unclear is, well, which of these is more effective, and it seems to depend on which measure you're using. That being said, again, the students still preferred the flipped class to the problem-based lecture. So one thing that did come out is, again, this may be an assessment of what's being done outside of class, but for particularly the biology-based students, memorizing problems outside of class, a small number of problems, actually may be effective, more effective than trying to get them to understand theory and giving them homework to work on. The engineering students, however, definitely seem to prefer not to memorize. They preferred the flipped class even if it wasn't as effective for them. One issue that I brought up in the paper, study skills may be a factor for these students. The engineering students tend to be younger and less practiced, and they may not know how to study outside, or they may not do as well with memorization. It's not real clear why that was a factor. But for the engineering students, the takeaway is that there didn't seem to be a clear advantage between the problem-based lectures or the flipped classroom, but they preferred the flipped approach, so they preferred a more active approach than the memorization. And either approach seemed like they were better than interactive lectures. This year, the attempt was made to follow up and actually kind of combine the two approaches using a flipped class with the problems being given as lectures outside of class, and then they would study those and again take quizzes in class. Unfortunately, with the COVID issues, that became impossible to get a good assessment, so an assessment wasn't done on that, but I'm hoping that we are able to pursue that in the future. The conclusions that we came to were that there was no serious difference between a flipped class and a problem-based class, at least for the engineering students. They definitely preferred the active approach to lecturing in terms of the student evaluation scores. And the one thing also to throw in there is that normalized gain may not always be the best way to assess the effectiveness. Sometimes normalized gain may give a poor score, while the effect size actually shows a better outcome or result. And these are my references.